This is Math 251, Section 13.5b, Part 2. We're now going to take a look at our spherical coordinates and what surfaces have particularly nice simple equations in spherical coordinates. Probably not surprisingly, because of the name, spherical coordinates, the sphere itself has a particularly simple equation. If I have a sphere, x squared plus y squared plus z squared, is equal to some constant squared, we know from our study of quadric surfaces that this is just a sphere with radius c. With spherical coordinates, the whole left-hand side of this equation is just rho squared. So the equation of this sphere is rho equals c. If you think about that one, it makes a lot of sense. Remember, rho was the distance from the origin to the point, and every single point on the sphere is the same distance from the origin. So rho is going to be constant. All right, next we have our half-circular cone. Z is equal to c times the square root of x squared plus y squared. We looked at this one with the cylindrical coordinates, and it had a nice equation there as well. So there's my half cone, just the upper half because of the positive square root. And I'm going to go ahead and convert this now into spherical coordinates. This is the one that has the most algebra associated with it, and we're actually going to look for a little shortcut as a result of the work that we do here. Z, I can replace with rho cosine phi, and that's c times the square root of, and I'm just using these equations right now. I'll square this one to get the x squared, and I'll square that one to get the y squared. So that would be rho squared sine squared phi cos squared theta for the x squared, and then for the y squared, rho squared sine squared phi sine squared theta. These are almost the same. The only difference is the cosine and the x, and the sine is the y. All right, under that radical, I can actually factor out the rho squared sine squared phi, which would leave cos squared theta plus sine squared theta, which is really nice to see since that's just one. So this is going to simplify beautifully. The square root of rho squared sine squared is just rho sine phi. I can divide the rho out of both sides. If rho was 0, I'd just be at the origin. I wouldn't really have a cone. And then I'm going to divide by the sine of phi. So cosine phi over sine phi equals a constant. Or in other words, cotangent of phi is equal to a constant. Now, if the cotangent of an angle is constant, then the angle itself must be constant. So phi itself is equal to some other constant, whatever the inverse cotangent of c is. I actually really like both of these equations. This is considered the nice simple one. This is the constant surface, right? Here's a constant surface for rho, here's a constant surface for phi. But what's nice about this equation is it relates directly to the multiplier of c that was in the original equation. This is a lot of algebra and trig to run through. So when I have an equation like this that I know is a cone, I will usually go straight from this point to this point. And that will allow me to solve for my phi fairly easily, just by using an inverse cotangent. If you think about it, the fact that a cone has an equation that's a constant phi value also makes sense. Remember that phi is the angle from the positive z-axis. And for a cone, that angle is constant all the way around the cone. So phi equals a constant, gives us that half circular cone. Next, we have the two planes, the vertical half plane and then the horizontal plane. For the vertical half plane, I'm going to go ahead and do the algebra first this time. Again, I'm just going to plug in the y and the x, just using my conversion equations here. Y is rho sine phi, sine theta, and that's equal to c times x, which is rho sine phi, cosine theta. I'm going to divide out a rho from both sides and also a sine phi from both sides. So I have sine theta equals c cosine theta, or sine theta over cosine theta equals c. That means tangent theta is equal to a constant, and theta would be the inverse tangent of the constant, which is also another constant. This one shouldn't be a surprise to us. That was the exact same as the equation for a half plane when we were using cylindrical coordinates. If you think for a moment about this one, I have this half plane, almost like a door opening out from the xz plane. The fact that theta is constant is reasonable. No matter where I look on that door, it's the same angle from the xz plane, and therefore from the x-axis. So those are my three constant surfaces in spherical coordinates: the sphere, the cone, and the vertical half plane. The horizontal plane is not a constant surface, but it is one that comes up a lot. So I want to take a look at that one to finish this discussion of the surfaces. Once again, I'm just using my conversion equations. I'm going to replace the z with rho cosine phi. So let's see, if I were to divide out the cosine phi, rho is equal to a constant divided by cosine phi, or you could also write it as a constant times secant phi, is going to be the equation of a horizontal plane in spherical coordinates. It's not a constant surface, but it's not a bad equation either. And again, those crop up often enough, it's just a good one to look at. So there's that horizontal plane. All right, keeping those in mind, and whenever we see a combination of those surfaces, we know they work well in spherical coordinates. Let's go ahead and talk about integration with spherical coordinates. Just as we had to use different forms of dA for rectangular and polar and cylindrical coordinates, we're also going to need a different form of dV for rectangular and spherical coordinates. For rectangular, dV was dx, dy, dz. I'm not quite sure why I didn't put it in here, but let's squeeze it in. For cylindrical coordinates, dV was r, dz, dr, d theta. And we saw that r came from the geometry of the dV. Just like cylindrical coordinates had a little extra piece because of its geometry, spherical coordinates will as well. Once again, at this point, I am going to say I'm going to give you this, and you can either accept it, or if you'd like, you can look in your book where they actually derive this, but I'm not going to take the time for us to do that right now. In spherical coordinates, dV is rho squared sine phi, d rho, d phi, d theta. So if I have a function in spherical coordinates, I'm integrating it over some solid object d, integrating dV. The way I'll always set that up is to say, let's integrate our function. And then the dv gets replaced with rho squared sine phi d rho d phi d theta. So, keeping that in mind, our next example asks us to use a triple integral to find the volume bounded below by the xy plane and above by the sphere x squared plus y squared plus z squared equals 36. All right, the xy plane is a lower boundary, and this would be a sphere of radius 6. But since the xy plane is a lower boundary, I'm actually only going to bother to draw the top hemisphere because it's going to get cut off by that xy plane. So there we go. Sphere of radius 6 cut in half. Notice what I'm really trying to find the volume of this time is a hemisphere, a half sphere. And we already know how to do that using a geometry formula. I'm going to use this as sort of a check on our process, since I didn't really prove to you where that came from. We're going to do this with a triple integral, and then we're going to check it with the geometry formula, and hopefully we'll be able to see that this does seem to work, even if we haven't had it proven to us. So if I want my volume, I know I'm going to integrate the function 1 to find a volume, and for the dv, I put in rho squared sine phi d rho d phi d theta. As far as my limits of integration, starting from the origin, I'm once again going to think about imagining a radial spoke, but this time instead of a two-dimensional radial spoke, it's a three-dimensional one. At the origin, I'm already inside my object. So rho starts from 0. Sorry, I'll fix that in a minute. I exit my object on the sphere, and since the sphere's equation is really rho squared equals 36, that means that rho equals 6 is the equation of that sphere and becomes my upper limit of integration. Phi is the angle with the positive z-axis. I'm going to want to start straight up here at phi equals 0. And then I have to go down to the xy plane. So I'm going to stop here at phi equals a 90-degree angle, or pi over 2. So 0 to pi over 2 would be my limits of integration on the phi. For the theta, since I'm going all the way around, I would go from 0 to 2 pi, all the way around the x-axis. All right, let's evaluate. Theta does not appear anywhere in my integral other than the d theta. So I'm going to use the usual trick and pull down a 2 pi. And then doing the first integral is a d rho integral. I'll get a 1/3 rho cubed sine phi, evaluated from rho equals 0 to rho equals 6, d phi. Just to make this a little easier on myself, I'm going to take that 1/3 and I'm going to get rid of it here and put a 3 in the denominator out there. So I have 2 pi over 3 times this integral from 0 to pi over 2. And plugging in the rho equals 6, 6 cubed is 216 sine phi, minus plugging in the 0 is just going to give me 0. All right. I'm to the point where I can integrate on the calculator. Again, not a difficult integral to do, but always kind of nice just at the end to not have to do it by hand. The integral of 216 sine phi is 216. And let's see, 3 goes into 216 36 times. So 2 pi times 36 would be 72 pi. All right, so there's the triple integral method of finding the volume of that hemisphere. Let's go back now to probably around 9th grade or so and look at the geometry method for finding the volume of a hemisphere. Volume of a sphere in geometry is 4/3 pi r cubed. And so since I want a hemisphere, I'm going to divide that by 2. Let's see. Radius in this case, the radius of my hemisphere is 6. So I end up with 4/3 pi times 216, and I'm going to change that divided by 2 to a times 1/2. And if I just use a calculator to help me with a little of the arithmetic here, again, it's not so hard to do, but we get a little weary after we do all this. I'm going to take 4/3, multiply it by 216, and multiply that by 1/2. And I clearly did something wrong here. What was it?